Hello everyone, thank you so much for your interest in privacy deployment. This is a talk by myself, Patricia Thaine, co-founder and CEO of Private AI, Pieter Luitjens, co-founder and CTO of Private AI, and Dr. Parinaz, Sobhani, head of applied research at Georgian partners. So a very common question we get when we start talking about privacy is, what is privacy? And if we look at the definition that we find in the documents from the GDPR, it says that data privacy means empowering your users to make their own decisions about who can process their data and for what purpose. And intrinsic to data privacy is data protection. That's why you'll hear a lot of confusion between what is data privacy, what is data protection, what kind of regulations deal with which. You need a marriage between the two. Another common question that we get is, why is privacy important in the first place? Well, it's about maintaining customer trust, for obvious reasons. It's also about building better tech, which is one of the reasons why we went into privacy-preserving technology research and development. And essentially, privacy-preserving technologies allow you to unlock access to data sets that would otherwise be locked away because of the private information that they contain. So you'll have examples of this, for example, 2 different hospitals sharing information in order to make advances in genomic predictions about disease. It also grants peace of mind when you know that you're doing the right thing, and when you know that you're following all the regulations and you won't get fined for essentially misusing data or making it more vulnerable to data leaks, for example. Proper data privacy, which goes hand in hand with proper data protection, also goes hand in hand with data security. It makes it much easier to maintain data security when you maintain user privacy and proper data protection around your information. And another big plus is that we keep seeing signals that integrating privacy into your software is actually a competitive advantage. So you'll see this with DuckDuckGo, with spike in downloads whenever there's some sort of scandal with Google privacy. You'll see this with Signal when they integrated a new blurring feature into their app right before the Black Lives Matter protests, the spike in downloads at the very end. And yeah, it's just a recurring trend that you keep seeing across the board. So definitely something to think about. There are lots of privacy-enhancing technologies to choose from, including secure multi-party computation, homomorphic encryption, data de-identification, differential privacy, secure enclaves, and data synthesis. And it can often be really confusing about which one to choose at which point, what kind of support is available for each of them if you want to integrate them yourself. This talk is really about clarifying the decision-making process a little bit. It's a pretty complex decision-making process, so essentially picture a decision tree. We're going to go down just a few of those branches and explore what kind of technologies work for different problems. The very first question you should ask yourself when you're dealing with user information is whether you have a consent to collect and process their information. So if the answer is no, you do not have consent, go get consent, as it's required under regulations such as the GDPR, and that affects any EU citizen regardless of where they are in the world. Now, if you do have consent, you might ask yourself whether you're sharing the information with a third party or directly with a user or group of users whose data you're making predictions on. Now, we're going to go down that third-party branch. What if you want to share information with a third party? But if you want to go down that other branch, what if you're only dealing directly with the user or group of users whose data you're making predictions on? Then that part you can find in a decision tree on our blog. Now, if the answer is you want to share information with a third party, the next question you ask is whether you want to just share insights or whether you want to share a data set that needs to be visible. If the answer is insights, you're going to need to determine whether you're making generalizations over a population visible to that third party or whether you need user-specific predictions. Whereas if you need to share the data set, you're going to ask yourself whether you need the personally identifiable information that's within that data set, such as names, personally identifiable numbers, faces, or whether the data can be useful without that PIR. If you need the PII, you should have a data processor agreement in place, encrypt in transit, and keep track of who you shared the data with and what they are using that data for. These are requirements under the GDPR. So you need consent for whatever you're using that data for. You need to keep track of where the data are, and you need to keep track of what they're being used for, all under the GDPR. And if you fit under this use case, you should also consider whether you might be a good candidate. This use case might be a good candidate for secure multi-party computation. So secure multi-party computation allows multiple users to share obfuscated inputs, and only the outputs are visible to all of the parties. So this is a great technology if you are okay with some communication cost, and if you aren't going to be tweaking the algorithms very often. So essentially you have to have a preset architecture. Otherwise, you're going to need to go in and potentially change the circuits every time that you need to make a tweak. Now, if you don't need the PII, you're going to ask yourself whether you're dealing with structured data with a predefined format or unstructured data such as text, images, video, or speech. If you're dealing with structured data, some of the options that are available to you are using data aggregation plus differential privacy. For example, for location data privacy, this is a great tactic. Or you could choose to use risk-based data de-identification or risk-based data synthesis. So these should always be combined with encryption in transit, and ideally encryption at rest as well, just for that extra layer of security, and also strict access controls. So privacy technologies are very much like security technologies. You're not going to get 100%. 100% is a myth. You won't have an antivirus that stops all possible viruses from getting into your computer, but you can still buy an antivirus and add extra layers of protection to prevent any harm coming to you or to your organization. So with data protection technologies, privacy enhancing technologies, the more you consider around access control, the more you consider around how much obfuscation you can add to sensitive data, the better. If you're dealing with unstructured data, very similar. You can choose to use risk-based de-identification or risk-based data synthesis using AI. So both of these methods should be using AI and not regular expressions. And it should also be combined with encrypting in transit, encryption at rest, and strict access controls. Data de-identification, in a way, can also be that extra layer of strict access control where only some people get access to the sensitive information and other people get access to the de-identified data. Okay, so we went through a lot of technologies, including differential privacy, de-identification, under which anonymization and pseudonymization fall, and data synthesis. So differential privacy has mathematical guarantees of privacy depending on the amount of noise that you add to the result of a query to a data set, for example, or to the amount of noise that you add during differentially private gradient descent when you're training a machine learning model. And often there's an accuracy noise trade-off. So if you are querying a data set, adding a certain amount of noise, you will get less and less precise results about your data set. But in the terms of machine learning models and using differentially private gradient descent, there's some research that shows that if you get the right level of noise, this accuracy noise trade-off does not necessarily exist, especially if you're training your data on specific information that you don't want it to memorize and wanted to make generalizations about what happens across multiple users and then deploy that model in the wild where those oddities don't occur as much. In terms of de-identification, make sure that if you are doing de-identification, you're using strong identification risk metrics. A lot of bad press has gone around anonymization because people do not use the term appropriately, and because a lot of the times when companies say they have anonymized data, they have absolutely not anonymized data and have left very clear personal identifiers within the data sets. In some cases, they're less clear than others. So for example, the Netflix IMDb scandal, where there was cross-reference between reviews from Netflix and IMDb, that was based on timing of when reviews were posted. So it is important to be careful with that and talk to experts about what you're doing there. So this is one problem that we're solving for unstructured data specifically at Private AI. Essentially, yeah, it's highly accurate, and it is very low latency and runs directly on premise or on device, and super easy to integrate with 3 lines of code. Shameless plug. So for data synthesis, if you do want to integrate data synthesis to create data that you can use for training your models, for getting insights about a population without having to specifically look at the details associated to a one individual, then you should also have strong risk metrics for re-identification for that. And it is often better to get a third party to work on it too. So if you are looking into this specifically for healthcare data, there's a great company called Replica Analytics that is under the direction of Professor Khaled El-Imam that I'd recommend you take a look at. Okay, so let's go back to the decision tree. Let's go back to, do you have to share insights or share a data set that needs to be visible? We went over the dataset branch. Now let's go through the insights branch. If you have to share insights, the next question you ask yourself is, are you making generalizations over a population or user-specific predictions? If you're making generalizations, you're going to ask yourself if latency is a critical requirement or whether computations can take a little longer and be approximated using polynomial operations. If low latency is a critical requirement, or if your operations can't be approximated using polynomials, you'll want to use trusted execution environments such as Intel SGX, and these are pretty much available in any modern Intel chip, and also you can find them on the Microsoft Confidential Compute Cloud. If you can wait and you can make approximations that using polynomial operations, you can consider using homomorphic encryption, and homomorphic encryption allows you to perform computations on encrypted data. So suppose you're a user who's encrypting your information, sending that information to the cloud is processing it in the encrypted domain, sends it back to the user, and the user decrypts it, and without the cloud ever being any the wiser of what information was sent over. So move back up the decision tree. Are you making generalizations over a population or user-specific predictions? Let's go to user-specific. So then you're faced with a question, are the other parties contributing sensitive input data, or can you compute the output without additional sensitive information? So if you need other parties' input, can you afford higher communication costs and have repeatable algorithms to run? This comes back to secure multi-party computation if the answer is yes. Now, if you cannot afford higher communication costs or do not have repeatable algorithms to run, so if you need to make lots of tweaks, or if sometimes the communication is cut off between you and the people whose data you need, then what you're going to have to do is get a data processor agreement in place, encrypt in transit and at rest, and have, once again, very strict access controls to this data. If the decision tree was not enough to help you determine whether to use homomorphic encryption, secure multi-party computation, or trusted execution environments for your use case, here is a bit of more of a breakdown of what kind of trade-offs there are with each of these technologies. So quantum safety is guaranteed by homomorphic encryption and secure multi-party computation. That just means that they're based on schemes that have not been broken by a quantum algorithm yet, not that there cannot exist one. For homomorphic encryption, you can still reverse engineer model weights based on the outputs, If you're training machine learning models, same thing for secure multi-party computation. You also can reverse engineer training data, so you might want to combine them with a differential privacy if you're using one or the other in machine learning, specifically differentially private gradient descent. Of course, you can use them for multiple other things than machine learning. Homomorphic encryption works straightforwardly enough if you're implementing polynomial operations. You can have alternatives or approximations of non-polynomial functions, popular ones like ReLU and sigmoid for machine learning if that's what you're looking to use it for. And there are plenty of libraries out there that you can use to integrate homomorphic encryption into your software, including Palisade out of the New Jersey Institute of Technology. There's Spark FHE that helps you interface with Microsoft Seal, and that's out of the Rochester Institute of Technology. There's HElib from MIT. Unfortunately, there wasn't enough space here to go over each one of them, but please feel free to email me if you have questions. And in terms of computational complexity, if you're properly parallelizing and if you're properly converting your regular algorithm into the homomorphically encrypted space, then you should be getting 3 to 4 orders of magnitude difference in compute cost. As for secure multi-party computation, the communication cost grows linearly. You don't have to deal with communication costs with homomorphic encryption, but the computation costs for secure multi-party computation are approximately linear in the depth of the circuit that you're building. So as I mentioned, you're going to likely build garbled circuits for secure multi-party computation, and those can be complicated to modify, so you have to have a preset algorithm in mind for you to build one. OpenMind is working on making a production-ready library for integrating secure multi-party computation into privacy-preserving machine learning. Okay, so trusted execution environments. There are no mathematical guarantees possible for trusted execution environments because it's a hardware-based solution. That is just much too complex to get mathematical guarantees of privacy for. And you also can have an adversary who reverse engineers model weights if you're dealing with machine learning models or training data as well. So also something to consider differential privacy for. SGX is available, as I mentioned, on most Intel chips currently deployed in modern computers, and you often need to combine this with oblivious RAM in order to avoid attacks that are based on code branching information that might show you different access patterns can tell you what kind of branch your code took in an if-else statement. If the batch size, the size of the information that you're sending to your secure enclave is small enough, then the computational cost can be lower than 1 order of magnitude, which is pretty awesome. Okay, so that was a lot of information. There's still a lot more to share about privacy technologies, but happy to answer those questions if you have any. The takeaways that we'd like you to get out of this talk are that, 1, privacy is possible, and it is possible to protect users' data while continuously making that data practical for different tasks. But the key is finding the right technology to do so. And privacy is also practical because you're not only maintaining customer trust, you're lowering the risk of data protection and data privacy fines, and you're gaining a pretty significant competitive advantage in certain cases, and you can also often get access to more data. So thank you for attending the talk, and feel free to follow us on Twitter. Private AI also has a blog, and we're going to post the decision tree to that blog if you want a more complete version of it. Please, any questions that you have, feel free to either ask them now or contact us later.